for our advanced user. You might interrogate or negotiate the requirements and find ways to structure the code to make errors either impossible and also make testing simpler and richer. This means that you'll have tests that are easier to reason about, easier to read through, and in concordance with your tests being easier to read, your code should also be easier to read as well. So, in this approach, what we're going to do here is we're going to, as an advanced user, rely on a few more Python mechanics that might not have been apparent to our intermediate or our beginner user. First and foremost, we're likely going to have better knowledge and understanding of the standard library in Python. We'll add a little bit more structure to our code by using the name tuple, and we'll intelligently use our cache property because our name tuple is, of course, immutable, so all properties on it don't need to be recomputed. In this case, I'm going to be taking advantage of some of Python's object model methods, or double underscore methods as they're often called, and I'm going to use our cache property decorator as well as our match case statements and even our unpacking syntax, as well as our namespacing of our overall parent class. Now, this part isn't as interesting as the others, so let's dive into the code. We're going to construct a payments from some portion that is equal and some portion that is unequal. You can see here what we have done is we've actually embedded some understanding about the nature of the problem into the code itself. We've identified that something very useful that we'll want to often do is determine, is this payment evenly splittable or is it not? And if it isn't, what is that unequal component and what is that equal component? Now, this is very different to how we wrote the code previously. Previously, we returned our dictionary mapping each guest to how much they have to pay. And you can think, well, this could also be an important thing to know, because if I go to dinner and I'm splitting the bill with another person or a group of people, well, I would just be interested in, well, how much do I have to pay? And so what we can do here is we can use convenient functions in order to reach into our fairly nested data structure and create convenient aggregations. And so what you can see here is our total is simply going to be reaching into each of these parts to help us compute the total without having to have that code repeat itself all over my program. Additionally, for backwards compatibility, I can create an asDictionary function that takes the current state of my object-oriented code and actually returns a dictionary that maps each guest to the amount that they have to owe. And this will get you one-to-one parity with what we had written previously. So as an advanced user, I am also concerned with backwards compatibility. Now, since this is hidden behind an asdict method, I might need to release a major version bump or something of that nature, since this won't be fully backwards compatible, but you can opt in and you can actually rewrite your code in such a way that all of your previous code will work. Finally, I'll use an object or a class construction method or a class constructor to actually create a convenient way to instantiate this object. And here you can see I'm again using our match case in order to find some different edge cases, as well as my match case to figure out, well, is it just an equal payment? Is there an unequal payment, or is there really no payment on either way? And you can even see how explicit we're being with, here is an example where we had no guests and no remainder. Here's an example where we had some guests and a remainder of 0, meaning the bill is split equally, and we're only instantiating the equal part of this class. And then finally, we're splitting the bill unequally, and you can see that we're instantiating both halves of this problem. Finally, as an advanced user, we might be a little bit more knowledgeable about the floating point arithmetic being done, and we'll have ways that can help us try and get around it if our values are too large or we lose precision. Now, our advanced code should be more readable, it should be more extensible, more flexible, or more testable. It won't necessarily be all of these things, but it should be at least some. The code above reduces some of the assumptions that we made in our original test. Remember the boundaries that we put on floats. No infinities, no nands, only positive values. Well, we might encounter a bill where these values occur not as the bill itself, but maybe as some part of a data processing pipeline. It's very reasonable to assume that by the time we get the data, we have actually altered the values so slightly, maybe in a logging or recording process or some other automated fashion, that we might introduce infinities or nands or negative values by mistake. And our code can actually help us catch that and identify what should be the correct route to take when we encounter these values. And so with our use of hypothesis as an advanced user, I'm simply going to break apart my tests into a few different pieces, and then we'll see how those compose to provide end-to-end coverage. For example, instead of just testing my function as one, or testing my program as one entity, I can break this apart. I can test my conversion logic going from dollars to cents or cents to dollars and assert that the total bill that's being paid is going to be equal to my conversion here. Additionally, if I want to test my API, I can actually factor out my smoke test. Remember, my smoke test was just given some known inputs. What does my function produce an expected output? And in this case, I'm actually using this to not just perform a smoke test, but also to test my API. Meaning that if I go back and I change some portion of my API to be something else, maybe I decide to swap out the name unequal to not equal for some reason, I have my API test here asserting what portions of my program or what portion of my objects actually exist. Finally, we have our actual test. This is going to be most closely matched up with what we've seen before. But because of the way that we have factored our code, we can actually make a little bit more sense of these tests without needing to drop so deep into the meaning. Specifically, you can see that if I have a bill and no guests, reads like English, well, we're going to assume that whatever payment is calculated, that's going to raise an error. If we have some financial value and no one to pay it, well, we're going to hit some type of exception, like a zero division error. And we can assert that Python will catch this and that we're actually going to test this and make sure that this exception occurs. Additionally, you can see that once we create our payments object, it becomes very easy to start working with different portions of our payment. I can test that our bill, right, is going to be equal to the total payment, where a lot of the logic intertwined about creating that total payment is abstracted away from me and taken care of by the object itself. Additionally, I can make the assertion that, well, if I have guests in my payments, well, all the guests who are part of the payment should have been guests who were at the meal, and I can assert that. Then I can introduce modalities into my test, and I can say, well, if I do have guests, I'm going to assert that our equal payments is not none, meaning we have some equal component, and this is to effectively say that the equal portion of our object was created and instantiated. Then we can go even further than that. We can say if there was no unequal portion, meaning all we had was an equal payment, well, we can make an assertion about that portion of our equal payment as well. Then we can say if we do have an unequal portion, well, what we can do here is we can reintroduce our assertion that the equal payment is not none. We've tested this once, so we might be able to get rid of this and refactor that, but we can perform all of our unequal payment tests here. We can say that, well, the guest who's making the unequal payment should not be part of the equal payments guest because nobody wants to pay twice. We can also say something like the unequal payment amount should be greater than the equal payment amount, right? If you're left footing that extra penny, you should be paying more than everyone else. And then finally, we should assert that the difference between the equal amount and the unequal amount is less than the number of guests, because you're never going to pay more pennies than there are guests if you're paying that extra unevenly split portion of the bill. But I will say this. As an advanced user, you know sometimes when you've written a little bit too much code or you've added too much complexity. And so as an advanced user, we also may know when the simple answer, though imperfect, might be the most expedient. For example, personally, when I go out to dinner and I think about splitting the bill, the only thing I concern myself with, well, Every time I go out to dinner, James is going to pay. So thank you very much, James, for all those times that we haven't dined together and that you have paid for my meal. Thank you everyone for attending. This has been an absolute blast approaching this problem, this seemingly innocuous and very straightforward problem of splitting a restaurant bill from the perspective of a beginner, from the perspective of an intermediate, and finally the perspective of an advanced Python user. We've talked about the different structuring techniques we would use to model this problem and how we would even test this problem using tools like PyTest and Hypothesis. Now, if you want even more about this problem, I urge you strongly to come check out James's seminar when he adds yet another wrench to our bill splitting problem here. Specifically, we're going to address, well, what if Alice only gets drinks and then Bob only gets food, and what if Charlie gets both food and drinks? How do we go about splitting the bill then? Thanks everyone. I hope you had fun, learned a lot of Python, and can implement these practices in your own work, and I'm looking forward to seeing you all next time. Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.